Welcome to the Explainer. Okay, let's dive right into this and kick off our investigation into why massive, seemingly indestructible structures sometimes just break. We rely on these engineered marvels every single day, right? So today we're exploring the fascinating and sometimes terrifying world of fracture mechanics.
Now, think about this. Have you ever struggled to tear open a plastic candy wrapper? You know the deal. You pull and the plastic just stubbornly stretches. But then you spot a tiny little cut on the edge, a notch, and boom, suddenly, with almost zero effort, the whole thing tears wide open. Why is that? Well, that exact mundane phenomenon is actually the core tenet of fracture mechanics. And applied stress gets massively amplified right at the tip of a tiny notch or incision.
So let's scale that candy wrapper analogy all the way up to some real life or death scenarios. On one side here, we have an oil tanker that completely fractured in half. How does a massive ship just snap? It all started as a tiny notch. As the sea buffeted the tanker, stress amplified at the tip of that microscopic flaw until a crack literally ripped around the ship's entire girth, snapping it like a twig. On the other side, that's Aloha Airlines Flight 243, a Boeing 737 that suffered an explosive decompression mid-flight. The culprit? Metal fatigue, aggravated by microscopic corrosion from flying in salty, humid air. Tiny flaws? Catastrophic failures.
I really want to let this quote from the text just hang in the air for a second. Brittle fracture occurs suddenly and catastrophically without any warning. No warning. That is exactly what design engineers are up against. It establishes the incredibly high stakes of our investigation today. Before we can figure out how to stop material failure, we really need to look at the primary suspects causing it.
Section 1. Ductile versus brittle fracture.
In the engineering world, materials are essentially classified by how much they can stretch or bend before they finally give up and break. So the crucial point here is understanding the difference in how these materials actually fail. Ductile fracture, we consider that the good failure. Why? Because it actually gives engineers a warning. The material goes through extensive plastic deformation, it absorbs a ton of energy, and the cracks are what we call stable, meaning they won't grow any further unless you actively force them to by adding more stress. Brittle fracture, though, is the bad failure. It happens with absolutely zero warning, little to no deformation, low energy absorption, and the cracks are completely unstable. Once they start, they just spread spontaneously and catastrophically. Let's take a look at what this ductile failure actually looks like to the naked eye. This is a macroscopic view of a ductile cup and cone fracture, the most common type of tensile fracture profile you'll see in ductile metals. Notice how one side is hollowed out like a little cup, and the mating surface is pointed like a cone. It's a dead giveaway that the metal was stretching and pulling intensely before it finally snapped.
Okay, let's move to and see how this builds step by step. The cup and cone fracture actually happens in 4 very specific physical stages. First up is necking, where the material just starts to narrow right in the middle as it's being pulled. Second, tiny microscopic cavities, called microvoids, form inside that narrowed section. Third, as you keep pulling, those microvoids coalesce. They literally merge together to form an internal crack. And finally, that crack shoots around the outer perimeter, shearing off at exactly a 45-degree angle.
Section 2. Microscopic clues in the metal. Let's zoom in a bit.
To really understand why these cracks start, we've got to go way deeper. When we interrogate the metal under a scanning electron microscope, magnified like 3D 300 times, the fibrous central region of that ductile cup and cone fracture reveals these incredible textures. Look at those tiny spherical dimples. What you're actually looking at are the separated halves of those microvoids we just talked about. The metal pulled apart, the voids stretched to their limit, and they finally tore, leaving these little crater-like dimples behind. And this brilliantly illustrates the stark contrast when we switch over to a brittle fracture. Zooming back out to a macroscopic view, you don't see any of those fibrous dimples or stretched-out metal. Instead, you get these sharp, V-shaped chevron or fan-like markings. These lines are amazing because they act like giant physical arrows left behind at the crime scene. If you follow them, they point directly back to the exact microscopic initiation site where that fatal crack began. Now, when we zoom in on that brittle material with our electron microscope, we see something called transgranular fracture, or cleavage. The crack propagation here is so incredibly rapid and unstable that it literally just snaps the atomic bonds and slices straight through the material's structural grains. That's what creates this flat, faceted, almost rock-like texture you're seeing here.
Alternatively, we sometimes run into this. An intergranular brittle fracture. Notice how totally different this looks? Instead of slicing right through the grains,
The failure sneaks around the three-dimensional boundaries of the grains. This usually pops up when some external process has chemically weakened or embrittled those boundary regions, essentially turning them into the path of least resistance for a runaway crack.
Section 3. The danger of stress razors.
So, we've seen what fractures look like up close. But why do these microscopic cracks actually cause massive steel structures to fail at stress levels way below their theoretical strength? Enter the stress razor. It's basically a microscopic flaw, an internal void, a sharp corner, or even just a tiny surface scratch. Remember our candy wrapper? That little notch is a stress razor. In massive structures, these hidden tiny flaws dramatically amplify the applied stress, concentrating it to deadly levels right at the tip of the flaw. And man, this effect is exceptionally dangerous in brittle materials simply because they can't yield and redistribute that stress.
Section 4. Calculating fracture toughness.
Because these microscopic flaws are literally always present in real-world materials, engineers desperately need a mathematical blueprint to predict and prevent these catastrophic failures. That's where fracture toughness comes in, represented by the variable Kc. Fracture toughness is basically a vital property that measures a material's resistance to brittle fracture when a crack is already sitting right there. It's a complex equation for sure, but at its heart, it relies on figuring out the critical stress needed for a crack to propagate, combined with the length and the geometry of the crack itself.
Now, what's really interesting about this slide is just how unbelievably small these margins of error can be. The text gives us this mathematical example using a relatively large plate of glass under tension. They calculate the maximum length of a surface flaw that the glass can handle before shattering completely. The answer? 8.2 micrometers. Just think about that for a second. A single microscopic flaw, totally invisible to the naked eye, measuring just 8.2 micrometers long, is all it takes to trigger a rapid, catastrophic fracture. Which leaves us with a truly fascinating, if maybe slightly unsettling, final thought for today's explainer. If a microscopic flaw, measuring just 8 micrometers, can literally be the absolute deciding factor between structural safety and an explosive, catastrophic disaster, what unseen cracks and stress razors are hiding in the engineered structures, bridges, planes, and buildings around you right now? It definitely makes you look at the solid world around you with a newfound, maybe slightly nervous curiosity. Thanks for joining me on this explainer, and keep questioning the mechanics of the world around you.